In this section, steady-state AC circuits will be discussed. The AC signal employed here will be a sine wave. Some discussion of transient effects will also be discussed where DC power is turned on and off in a circuit that contains a capacitor or inductor. Common AC circuit symbols consist of resistors, capacitors, inductors, transformers, and AC power sources. Capacitors and inductors store energy in a circuit. As a circuit operates, these energy-storing components exchange energy with other components in the circuit. Ohm's law is used in AC circuits to predict currents and voltages just as it was applied to DC circuits. The application of Ohm's law to steady-state AC circuits is illustrated in this slide. 3 new terms are defined: inductive reactance, X sub L, capacitive reactance, X sub C, and impedance, Z. How these terms relate to inductance L, capacitance C, frequency, and each other is presented in equation form on this chart for your review. Inductive reactance is the opposition to the flow of current in a circuit due to an inductor. Note that inductive reactance is directly proportional to the inductance in henries and the frequency F of the applied excitation. Capacitive reactance is the opposition to the flow of current in a circuit due to a capacitor. Note that capacitive reactance is inversely proportional to capacitance C and the frequency F of the applied excitation. Impedance is the opposition to the flow of current in a circuit due to the combined effects of resistance, inductance, and capacitance. Inductance is the ability of an electric circuit or component to oppose any change in current flow. The ability of the current to oppose changes in current is due to its ability to store and release that energy that has been stored in a magnetic field. When direct current is initially applied to a coil or inductor, a magnetic field builds up when the circuit is energized. Expansion of the magnetic field cuts across the coil windings, causes a counter voltage to be induced in the coil. This counter voltage tends to oppose the original applied voltage. Once the current reaches its Ohm's law value, it remains constant and the inductive effect ceases. If the DC voltage applied to the coil is switched off, inductance occurs again. When the switch is open, there will be a noticeable arc at the switch contacts. As the current falls to a zero value, the collapsing magnetic field causes a high voltage to be induced in the coil. The arc produced at the contact is a result of the induced voltage attempting to maintain current in the circuit. Inductance is present only when the current changes. In a DC circuit, this occurs each time the circuit is switched on or off. The inductive effect just described takes place in the coil itself and is called self-inductance. If a second coil is magnetically linked to the first, the inductive effect will also be felt in the second coil. Mutual inductance is the term used when the effect of induction is such that current change in one circuit produces an induced voltage in another circuit. This is the basis for transformer operation. Note that this is the transfer of energy from one coil to another without there being a direct electrical connection between the two circuits. It is a result of mutual induction. An easy way to determine if an inductor is open or shorted is to make a DC resistance measurement with an ohmmeter. Normal resistance values depend on the wire size, the diameter, and the number of turns, the length of the wire that makes up the inductor. This is an example of computing inductive reactance X sub L in a circuit. X sub L equals 2 pi FL, where X sub L is the inductive reactance, pi is 3.14, F is the frequency in hertz, and L is the inductance in Henry. In this example, the inductive reactance equals 2 times 3.14 times 1,000 hertz times 0.2 Henry equals 1,256 ohms. The transformer is a device which changes alternating current to different voltage and current levels. Some of the many uses for transformers include their use in long-distance power distribution systems, power supplies, impedance matching in audio and RF systems, ground isolation, and automotive ignition systems. A transformer is a device used to transfer electric energy from one circuit to another by the principle of mutual induction. Transformer power output equals transformer power input minus the internal losses and is the product of voltage and current. The average efficiency of a transformer is over 90%, so for most practical situations, it can be assumed that the transformer is an ideal transformer. There is no gain or loss in an ideal transformer. energy is transferred from the primary circuit to the secondary circuit. This means that the volts multiplied by the amperes of the primary circuit equals the volts multiplied by the amperes of the secondary circuit. In other words, in an ideal transformer, the power output must equal the power input. The maximum power rating of a transformer is often included on the transformer specification plate. Transformer power is rated in volt amperes, VA, and not in watts. This is because the transformer power is apparent power. It does not convert the power to heat, but merely transfers the power from the source to the load. The ratio of the number of turns in the primary to the number in the secondary is the turns ratio of a transformer. The voltage ratio of a transformer is equal to the turns ratio. This is an example of a step-up transformer because there are more turns in the secondary winding than in the primary winding. The turns ratio is 2, therefore the secondary voltage will be twice the primary voltage. This is a step-down transformer because the primary winding contains more turns than the secondary winding. Since the turns ratio is 20 to 1, the secondary voltage will be 1/20th of the primary voltage, or 12 volts in this example. This is a step-up transformer where the turns ratio, secondary voltage, and load resistor are given. The question is, what are the secondary and the primary currents? The secondary current can be found from Ohm's law, where I equals V divided by R, or I equals 60 volts divided by 25 ohms equals 2.4 amps. The primary current can be found from the secondary current multiplied by the turns ratio.